Good morning. In today's session, we will find out what is the torque acting on a rectangular current loop which is placed on a uniform magnetic field. We know that when a current carrying conductor is placed in a magnetic field, it experiences a force. Now here we have a rectangular current loop. So when I say a rectangular current loop, it will have four sides. So four sides, current carrying sides. So the force will be acting on each side. So once you calculate the force on each side, you will be able to find out what is the total force. Is there any total force or is there any torque? So first we'll consider a very simple case. I will consider a rectangular loop placed in a magnetic field. So let me draw the diagram. So here first we'll consider a magnetic field B. So let us say we have a magnetic field something like this. This is the magnetic field B, and you are placing a rectangular current carrying conductor in this field. Now let us say you can assume any direction of the current. Here I'll take anti-clockwise direction of the current, and the current I is flowing through this rectangular loop. The sides of the loop, let us say this side is A, and this side is B. The rectangular loop of carrying current I is placed in a magnetic field B. Now we will find out what is the force on these sides. So for that case we will mark the sides. Let me say this is side number 1, and then this is 2, 3, 4. And in this case, how we have placed, as I said, we are considering a very simple case. The plane of the loop is placed in such a way that it is parallel to the magnetic field, or if you see, the magnetic field B is along the plane of the loop. So as shown in the figure, we will consider a very simple case. The magnetic field is lie in the plane of the loop. Now we will write these things. So consider a rectangular loop carrying current I is placed in a magnetic field as shown in the figure. Consider a rectangular, consider a rectangular, or I missed. Consider a rectangular, consider a rectangular loop carrying current I is placed in a magnetic field as shown in the figure. Now here we have placed the loop in such a way that the plane of the loop is along the direction of the magnetic field, or B is in the plane of the loop. The loop is placed in such a way that the uniform magnetic field B is in the plane of the loop. That is, they are parallel to each other. Now because the plane of the loop is parallel to the magnetic field, if you see, the forces acting on sides and 1 and 3 will become 0 because these sides are parallel to the magnetic field. So in our force equation, F is equal to BIL sine theta. The theta, the angle between the magnetic field and the length of the loop, that is I can say that the current carrying side, that will be 0. So cos 0 is sine 0, because it is FBIL sine theta, sine 0 is 0 and hence the force is 0. Because the sides are parallel to the magnetic field, the force becomes 0. So we can write those points here. The field exerts no force on sides 1 and 3 because these sides are parallel to the these sides are parallel to the magnetic field. So forces acting on side 1 and 3 is 0 because F is equal to BIL sine theta. Theta, the angle between the field B and the side of the conductor or side of the loop is 0. Because if the field B is in this direction, the current carrying line is also in the same direction. So the angle between these two is now 0. That is why in the equation sine theta becomes 0 and hence force is 0. So now forces acting on sides 1 and 3, we wrote it as 0. The field exerts no force on sides 1 and 3 because these sides are parallel to the magnetic field. Now the other two sides, if you see, they are perpendicular to the magnetic field. The sides 2 and 4 are perpendicular to the magnetic field. Now we have to find out what is the force on these sides. So the sides 2 and 4 are perpendicular to B and hence there exists a force on both these sides. So there is a force acting on side 2 and 4. We have to calculate what is this. What are these forces? So let us say the force acting on side 2 is F2. So let the force acting on side 2 is F2. So now we have to find out direction of F2. Now you can use the Fleming's left hand rule to find out the direction. If you use that, you will get the direction of the force is normal to the plane of the paper and upward direction. So the force will look as though it is pointing towards you. I will draw it here. So the F2 will be acting upward direction. So here, though I have shown here it as upward direction, actually this force is acting towards you. So I will show you how it is actually acting. So here imagine this is another 3D picture, but here it is the clockwise current. So now I am considering anti-clockwise direction of current. So here I have marked the force is going into the plane of the paper. But in our case, we have assumed the opposite direction of current. So the force will be upward direction, means it will be acting like this. So you have to write the force like this. So here in 2D I have just shown it as in the upward direction, but actually the force will be acting like this, perpendicular to the plane containing the B and the current carrying conductor. So F will be acting like this, upward direction. So let the force acting on side 2 is F2. So this force is directed, this force is, or I can write normal to the paper, plane of paper, and upward direction. Now the magnitude of the force will be equal to BIL. So B into I into the L, side is A. So you can calculate the magnitude of the force here. So this will be equal to F2 we have the force equation is F is equal to BIL sin theta. BIL sin theta. So B is B the current and I, and what is the side? L is the length is A, and it is sin 90, that is 1. So this will be equal to BIA. F2 is BIA. Similarly, find out the force acting on side 4. The magnitude of the force will be same. Let the force acting on side 4 as F4. This force as the direction will be opposite to F2. This force is normal to the plane of paper and downward direction. Downward direction. So here in the picture I will just show it as acting downward. I can mark the forces this as F2 and F2. So I'll show you how actually they are acting. So they are acting like this. So this is clockwise current. So the torque is the loop will turn like this as shown here, because this force is acting upward direction, this is downward direction. But in our case it will be reverse because we have assumed anti-clockwise direction. So the forces being equal and opposite and of same magnitude. So the magnitude of F4 is also same only. So you can write what is the magnitude of F4 is again it will be BIA only. Okay. So now the forces equal and opposite constitute a couple. So now this forces being equal and opposite constitute a couple, and hence there will be a torque acting on it. Now find out what is the torque. So this, now we have the forces, one force is acting like this, another one in the upper direction, and we know this is F2 and F4, and this being B. B is the distance between the force. So that is why torque acting on the rectangular loop is equal to force into distance. So force is BIA into B. Now A into B is the area of the rectangular loop. So I can write it as BIA. So the torque acting on a rectangular loop is given by BIA. B into I into A, because AB is equal to A, which is the area of the loop. Area of the loop. I will write A is A into B, which is equal to area of the loop. So the torque is given by BIA. B into I into A. So this is about the torque acting on a rectangular loop. Hope you understood this.